Section 11.4, Analysis of Variance, also known as ANOVA. In this section, we'll try to decide if the means of 3 or more populations are equal or not. And we might be interested in questions such as, is the mean number of minutes spent on an online review activity the same, regardless of what letter grade the student received on the final? Or maybe, is the mean home price the same for all the cities in a community college district? Or possibly, is there a difference in the true mean gross box office receipts for movies from several different genres? We'll attempt to answer these questions by comparing the amount of variation between the sample means from each population to the amount of variation in the samples themselves. And that's why this section is called Analysis of Variance. That phrase right there is a pretty tricky one. We'll see some pictures and explain that further as we move along. And despite the fact that variance should make us think of standard deviation, this will actually be a test about the population means. So variance is connected to standard deviation, but this is a test about the means. We get the name analysis of variance for the test because we're looking at the variation among the means. Again, it's tricky. We'll look at some pictures as we go through an example that will clarify that. ANOVA will also use a distribution that's new to us called the F distribution, and we'll have to calculate an F statistic, and then we'll also have to use that distribution to calculate the p-value. So that can be a little intimidating that at this stage we're going to see yet another distribution, but it turns out that the test statistic is pretty tricky to calculate, and so we're going to use technology for all these problems to both calculate the test statistic and the p-value. So despite the fact that we're using a new distribution, it's not going to be a hard one for us. We're going to be provided the information we need from technology. All right, let's go ahead and look over the procedure for an ANOVA test. I'm going to run through the whole procedure and talk about it a little bit in terms of the examples up above. But to really clarify what's going on in this box, we need to hit an example, which we'll start on the next page. So first of all, the requirements that we have are based on making sure the F distribution is solid so we get a good calculation of our p-value. And we need all the following things to be true for that. We have to have one categorical variable, which are the factors used to establish the populations, and then one quantitative variable, quantitative outcome variable or response variable, so that means can be calculated. So just a quick example of that. When we're looking at this idea of is the mean home price the same for all the cities in a community college district, the categorical variable would be the cities and the city names. So like for Chabot, we would have Hayward and San Leandro and Castro Valley and Union City and things like that. And actually it's the district, so maybe Livermore and Pleasanton and Dublin and beyond. And that would be our categorical variable, and then the quantitative one would be the home prices in those cities. The next factor is we must have independent random samples from 3 or more populations. So random, we understand that we should be randomly selecting. The independent can be a little tricky, and it doesn't apply to those examples so much, or it's hard to illustrate. Let's suppose though that we were going to randomly select people, and we wanted to look at the variables height, weight, and IQ, and we wanted to group people by ethnicity. Then for the variables to be independent, or for the samples to be independent, you're not allowed to pick a person and then use their height, their weight, and their IQ, because then those 3 things aren't independent. They're all kind of tied together. So if it was really going to be independent, you'd randomly select a person and get a weight, randomly select another person, get a height, randomly select another person, get an IQ, and you just keep doing that till you got the data, rather than having like these triples where all 3 factors are from the same person. And then the populations for each group should have the same standard deviation, so we want an equal spread in those populations. We'll only be looking at samples, so we'll do the best we can to judge if the populations have equal standard deviations or not. And then each sample should either be large or drawn from a normal population, and large will have that normal n greater than or equal to 30 idea. And a lot of times we don't have samples that big, so we'll need those normal populations, and we have kind of a quick way to assess that. All right, So the steps of the hypothesis are the normal 6 steps. The first 2 coming in the set up the test phase. Step 1 would be to determine H0 and H1, and both of those will always follow this format where HO says that mu1 equals mu2 equals mu3 equals and so on until we get to whatever the last number is. And then the alternative hypothesis will be that at least one of the population means does not equal another. So HO says they're all the same. H1 doesn't say they're all different. It says at least one is different from the others. If they're all different, H1 would be true. If just one is different, H1 would be true. The only way HO is true is if they're all exactly equal. So then step 2 would be to decide on a significance level. Like always, that'll be a simple step for us, just noting what it says, writing it down, being prepared to use it later. Then the second phase will be to gather and weigh the evidence, where we do step 3, calculate the test statistic, which is an F statistic, where we're trying to measure the variation between the groups and divide that by the variation within the groups. And technology is going to do that for us, but we will look at pictures and talk about it a little. When they talk about variation between the groups, they mean how different the means are in the groups compared to how different the data values are within individual groups. Again, a picture will help clarify that some. Step 4 will be to determine the p-value using technology. There's degrees of freedom for an F distribution, and there's 2 different kinds. There's the k-1 and the n-k, so they both get used, where k is the number of factors or groups and n is the total number of data values among the groups combined. We could sort that out, but honestly technology is going to do it for us, so it's not that big of a deal. And then the last phase will be decisions and conclusions. Step 5 being decide whether to reject or not, and as normal, that will be by comparing the p-value to alpha. And then we'll state the conclusion of the test in plain language using the words of the application. Rejecting HO means that we had enough evidence at the given significance level to convince us that at least one of those population means was different from another one. But when we do this for actual problem, we'd want to mix in the application into the language a little bit. All right, so there's kind of the theory, the procedure all kind of thrown at you real quick. Now we're going to go ahead and jump into an example and hopefully shed a little bit more light on what's going on. All right, here's our example. A farmer is testing the effects of 4 different fertilizers on the yields of a certain variety of tomato plants. The 4 fertilizers are randomly applied to each of 10 different tomato plants, and the number of tomatoes produced by each plant are recorded. The green vertical lines represent the mean for each sample, and the results of performing the ANOVA test using technology are shown also. So here's fertilizer A's dot plot. You can't see the color on this because I printed it in black and white, but that vertical line is the mean of fertilizer A, or the sample for fertilizer A. And then here's fertilizer B, the number of tomatoes for each individual plant, and then again the vertical line representing the sample mean for that fertilizer. All right, so let's go ahead and start looking at the questions. Here's the output for the test itself, and we'll use those pieces of information as we go along too. So part A, discuss the requirement that there be both a categorical variable and a quantitative variable in this problem. So the categorical variable would generally be some word factor. So that could be like brand names. In this case, they're kind of generic: fertilizer A, fertilizer B, fertilizer C, fertilizer D. But the categorical factor is the type of fertilizer. And then the quantitative variable is the one we're computing means for, and we're getting the mean number of tomatoes for the sample from each fertilizer type. So the quantitative variable is the number of tomatoes. And that's all right here, but it's the number of tomatoes for each individual plant. So we tested 10 plants with fertilizer A. One of them, it looks like, produced 39 tomatoes. This one, 36 tomatoes. That one, 35 tomatoes, and so on. So the variable is the number of tomatoes for each plant, not the average number. We'll use the average, but the variable is just for each individual plant. All right, let's take a look at part B. Discuss the requirement that the populations for each group should have the same standard deviation. So luckily for us, this is kind of a loose requirement, meaning that it doesn't have to be perfect for the test to work well. So as long as it looks like reasonable that maybe they could have the same standard deviation, we kind of proceed with the test. So this requirement of the populations all having the same standard deviation is considered to have been met as long as the largest standard deviation for any of the samples divided by the smallest standard deviation for any of the samples is less than 2. So let's check that out for this one. So we're going to have to use the output up above. In this chart, we see the standard deviations for each of the samples. So the largest one was for fertilizer D. It's about 4.143. So let's see. So because 4.143, let's go ahead and throw one more digit on there. It's a 2, but if we round it up, that would be a 3. Then we're doing the 5 digits we usually do for standard deviation. So there's the largest standard deviation for any sample. The smallest one looks like this 3.43 number, so we'll divide that by 3.4319. And in order for this to be over 2, the top would have to be more than double the bottom. If you double 3.4, you get 6.8. So I can see right away that that's less than 2, but sometimes it might be a close call. So what we could always do on these is just go to the calculator and work it out. So we have 4.1433 divided by 3.4319. We get about 1.207, with the key thing there being that that is less than 2, and so it appears that this requirement has been met. Okay, so this is our method of checking that specific requirement. Moving on to the next question, discuss the requirement that each sample should be large or drawn from a normal population. So this is also a loose requirement. So the large part, by the way, would mean n is greater than or equal to 30. So if we have that for any sample, we don't worry about what shape the population is. But a lot of times we won't have that. So then we're going to consider this requirement to be met as long as none of the samples have dot plots that are severely skewed. So you might remember that as being kind of our requirement for medium-sized samples, and that's what they apply here to all the samples regardless of how big they are, as long as they're from small, even small or medium samples, and they can do it because the requirement's a little looser here. We don't have to be as strict about it. So you go up and you look at the dot plots, and we have kind of maybe the most data right here and then some symmetry to that. Here we have a couple dots here, but I don't know if that's a real peak, and then it's kind of evenly spread, so it almost looks uniform except for that one extra stack here. Maybe this looks a little right skewed here with a lot of dots on this side, more spread out on the right, but not severely. Here again, that seems to be kind of a random stack. Other than that, it seems pretty uniform. So because none of the dot plots appear to be severely skewed, it appears that this requirement has also been met. So it has been met. And let's just go check back at the list of requirements and see if we covered it all. So we have the categorical variable and the quantitative one. We have done the loose requirement for the same standard deviation, the same with for normal populations. We didn't talk about the independent samples here, but we're not taking like multiple measurements from the same tomato plant, so we're not really having that issue of the samples not being independent. Every tomato plant is a sample from which we just get one piece of information, so the independence there is probably pretty safe, even though that wasn't addressed here. And when you're asked about the normal populations, there's two factors. If n is greater than or equal to 30, you're good for that sample. For samples smaller than that, as long as the dot plots don't make them look severely skewed, then we're okay there too. All right, so none of that's the actual hypothesis test. That's just checking the requirements to make sure that when we calculate our p-value, we get a reasonable assessment of probability there. So if we don't have the requirements met, the distribution doesn't fit, and our probability estimates will be off. So that's just a check on that. We still need to do the actual hypothesis test, so we'll turn the page and take a look at that. All right, so now we're going to jump in and start doing that hypothesis test, and this is where you kind of expect there to be a lot of work, but because we're going to be using technology, this is actually going to be a pretty quick part for us. So perform an ANOVA test at the 5% significance level to determine whether or not the true mean amount of tomatoes produced will be the same for all types of fertilizer. Show all 6 steps, but use technology to help with the test statistic and the p-value. I'm going to cycle some other pages here in front of you as we go through this. Our HO is always supposed to have this format, mu1 equals mu2 dot 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 mu sub k. That format, but it doesn't say exactly that. So what we're going to write here is mu1 equals mu2 equals mu3 equals mu4. We had 4 types of fertilizer, so we're going to say the mean of the first is the same as the mean of the second and the third and the fourth. It might also be a good idea on this one to, instead of do 1, 2, 3, 4, to do A, B, C, D. That would also be perfectly fine. I'm using the 1, 2, 3, 4 because that was what's shown in the procedure box. And then H1 will say that at least one of the population means does not equal another one. Alpha is our significance level given as 5%, so we'll write alpha equals 0.05. And again, in most of the hypothesis tests we do, once we get to, let's number these steps here real quick. There was step 1, step 2. Once we get to steps 3 and 4, calculating the test statistic and the p-value, that's where we expect to start having to do a lot of work. But technology is doing the work for us on this one. We have this output from StatCrunch here that says the F stat, so the F statistic or test statistic is 8.78. And let's go with 3 decimals like all of our other test stats, so a 3, 8.783. So we didn't really have to do anything there. That was just computed for us, and then so is the p-value. So here's our F stat right there, is step 3, and here's our p-value, which is step 4. So our real job on these, because we're always going to have these little technology outputs, or if we're doing a tech project ourselves, StatCrunch will produce this for us, is just to know where to find the test statistic and the p-value, and then also know how to interpret them, especially the p-value. So the p-value there was 0.0002. So this is step 6 down here talking about the evidence. So there's just a gap here, but step 5's got to go somewhere. So that would be right here, and we're trying to decide whether to reject or not reject HO. The p-value is telling us that if we were to reject HO, the risk of that being a type 1 error is 0.0002, which is smaller than 0.05. So that's a low risk, therefore an acceptable risk. So we will go ahead and say reject HO, and that it was an acceptable risk. And really what the p-value is actually calculating the probability of is if the means were all really equal, what is the probability that we would have got samples where the means turned out as different as they did in these samples. And the probability that if HO is true, we would have got picture like we did with means spread out like we did is really low. So that makes us doubt that HO is true, so we reject it with a low risk of being wrong. So we rejected HO, so there is enough evidence at the 5% significance level to show the true mean amount of tomatoes will not be the same for all types of fertilizer. Just to clarify a little bit, when we say it will not be the same for all 4 types, we're saying they're not all going to be equal. We're not saying they're all going to be different either. We're just saying at least one is different from the others. Okay. All right, so now, there was the whole hypothesis test. 1, 2, 3, 4, 5, 6, kind of banged that out nice and quick because usually we get bogged down in steps 3 and 4, but this time technology is doing it for us, so nice and quick. All right, let's look at some follow-ups to this now. Explain how your decision from the ANOVA test agrees with the variation or spread of the data and the means in the dot plots. So let me show you the picture and just talk through it, and then we'll come back and we'll fill in these blanks. So what we do with this analysis of variance is we look at how much variation is there in the sample means. So these two sample means are almost the same, so very little variation there. This one's a little bit different. That one's a lot different. But how do we really decide, like, is this a big difference? Is this a big difference? And the answer is we compare it to how much variation there is in the samples. So each of the samples has a fairly similar type of spread to it. And we saw that with the standard deviations. They're all fairly equal as well, fairly close to each other in size. So if you look at a difference like these two, that seems like almost nothing compared to how spread out the data is. When you look at the difference between this one and this one, that's a little bigger, but it's still kind of small compared to how spread out the data set is. Yet this one for fertilizer B compared to, say, fertilizer D, the distance apart of those, that spread, is almost as big as the spread of the whole sample for each of those samples we're seeing. So when you start to see means that are spread out from each other almost as much as the data spread is in individual data sets, that's where you're starting to think it's hard to believe that the real population means are all equal if there's this much variation in the sample means. A small amount of variation could just be random variation. But these big ones, we should be suspicious something else is going on, like maybe the population means aren't actually equal. All right, so let's see how we would write that up. The amount of variation in the sample means which is indicated by those vertical lines, not green on this picture, seems small. Actually, it doesn't seem small. It seems kind of large compared to the amount of variation in the individual samples. So since I messed that up in words, let's kind of look at it again. The amount of variation between these two means is small. Maybe even this is moderately small, but the amount of deviation or spread between this mean and that mean seems pretty big, pretty far apart compared to how spread out the data sets are. All right, moving on to the next one. Based on the dot plots, which fertilizers are you convinced have a different mean? So when we rejected HO, we said there's enough evidence to be convinced at the 5% significance level that they're not all the same. So that we're saying there's got to be one that's different in there somewhere. So let's push that up and bring in the picture. Let's see if I can fold this a little bit. Squeeze it in there a little bit more. So which one are we convinced is different? Well, these two look fairly similar. That one's not very far off. This is the one that really caught our attention as being kind of far apart from the other three. So there's barely any difference between the sample means for these two. So that was fertilizer C and D. The sample mean for one of them doesn't seem that far away. That would be this one. So the sample mean for fertilizer A doesn't seem that far away from the two mentioned above, C and D. However, the sample mean for this one, fertilizer B, seems substantially, let's see, it's a lot less tomatoes there. Like this is the number of tomatoes, it's a lot smaller. So substantially smaller, or lower, you could use that word also, than the other three means. Therefore, I'm convinced that the true mean for fertilizer B is different than the others. I'm saying this is too far away to just be random, whereas maybe this is. So really, the p-value is judging that. The p-value is saying one of them has to be different, or almost has to be different, based on that p-value. So which is the most likely candidate for that one? It's the one that seems furthest apart from the others when we look at the graph. All right, final question. What advice would you give a farmer considering these four fertilizers? So they're trying to decide which one of these should I buy and put on my crops, right? Let's assume the cost is all fairly similar. Well, I would advise the farmer to definitely not choose fertilizer fertilizer B, because fertilizer B is not only the one that's different, but it's different in that it produced less tomatoes. The farmer should probably avoid A. I don't know if we have statistically significant evidence that this one's worse than these two. The dip here compared to those could just be random variation. On the other hand, it does look lower in the samples. you might be tempted to tell them, oh, choose D for sure, but these are so close together. The fact that D turned out better in the samples could just be random variation. Maybe C is just as good. Really, maybe even A is just as good, but these two are the leaders in the samples. So I think the best choices would be either C or D, but it's hard to know for sure which of those is best. Don't get too caught up in the fact that D has a bigger mean. That's just in a sample of 10 plants. He's going to go put this fertilizer throughout a whole field, right? So what happened for 10 plants is a little better than for 10 more. That could be random variation. Either of those could be just as good. So maybe you could use other factors there based on price or something like that. All right, so that was a quick run through of what ANOVA looks like. I didn't hit every single detail about how ANOVA works. You can get a little bit more of that if you read the section, so you can find further details on checking the requirements for ANOVA tests and just other parts of the process as well. If you like the requirement we skipped, what was that one about? Independent samples. If you read the examples in the book, you'll see those too. So you can look at 11.4 for that. And then the parts about the requirements, we use a lot of times these like loose rules of thumb that I showed you in the examples. Those are summarized on the page just before the exercises in 11.4, so you might want to look at that too while you're doing homework. And then one other thing to consider, this was a problem where we ended up doing a reject HO. Might be nice for you to look at one where we do not reject HO as well, and there is an example of that in the book too. So if you read through section 11.4, you can get further detail, but through this video, you're getting a quick idea of how this works. All right.